Hi everyone, the last application of logs here, pH scales. Okay, if you, all my chemistry people here, you might have learned how to calculate pHs or comparing acids and bases or acids with other acids and looking at their relative, their hydrogen concentration. In 1909, Sorensen, a Dutch chemist, introduced the term pH, representing the expression the power of hydrogen. Interesting. pH, the power of hydrogen, to measure the extremely wide range of hydrogen ion concentration in substances. So, like orange juice or water or a soft drink, vinegar, battery acid, right? Look at all the different things on the pH scale. The pH scale measures the range of hydrogen ion concentration by determining the acidity or alkalinity um, of a solution. The scale measures from 0 to 14, with values below 7 representing increasing acidity and values above 7 representing increasing alkalinity. The value 7 represents the neutral level of on the pH scale, so water, where the solution is neither acidic nor alkaline. Okay, it's a handy little scale. Um, again, another area in science or natural phenomena where logarithmic scales really help us understand it better. Similar to the Richter scale, the pH scale is logarithmic. A difference in 1 unit of pH corresponds to a factor of 10 difference in intensity. This means that each whole number step represents a tenfold increase in intensity. Therefore, vinegar has a pH of 3. Where's vinegar? Right here. pH of 3. Okay, so if vinegar has a pH of 3, then it is 10 times as acidic. Remember, more acidic, acidity increases going to the left from 7. If vinegar has a pH of 3, then it is 10 times as acidic as tomato juice, which has a um, acidity of 4. Who likes tomato juice? I do not. I like tomatoes, but not tomato juice. Okay? This is a tenfold increase as I go this way, a 10-time increase um, of acidity. Okay? Um, Vinegar, which has a pH of 3, is a 100 times as acidic as normal rain, which is a pH of 5. Here's normal rain right here. So I'm going 2 units of pH. That corresponds to, so 2 units of pH corresponds to a 10 squared increase in acidity levels, which is like a tenfold increase in the concentration of the hydrogen ion measured in moles per liter. Okay. On the other hand, household ammonia, pH of 11.5, is 10 times as alkaline as milk of magnesia at 10.5. Okay, so when we go the other way, we said household ammonia right here. You might have some at home for cleaning purposes, right? This is a pH of 11.5. This is 10 times more alkaline than milk of magnesia. This is a 1 unit increase, 1 unit, which is a tenfold increase. Okay, here's my formula. pH equals the log of the hydrogen concentration, where pH is the acidity or alkalinity of a solution, and H plus is the hydrogen ion concentration, the intensity of hydrogen ion measured in moles per liter. So if you have a solution, right, that's acidic, you'll have a whole bunch of these hydrogen ions floating around, and that's what creates that sensation of, like, if you've ever had a can of soda, that's phosphoric acid, folks, or drink orange juice, that's citric acid, folks. Or if you've smelled, or like you put a little vinegar in as a sauce for like a dipping sauce. Oh, I love using vinegar as a dipping sauce with some soy sauce, green onions, um, Korean chili flakes. What else do I put in? Pepper, cracked pepper, and you put a dash of vinegar in there. It gives it that little bit of kick or acidity in that solution, and it's great for those Korean pancakes, or it's a great dipping sauce, right? That's hydrogen ions floating around in your solution, and that is what we are measuring when we're talking about pH, is how many of those hydrogen ions are floating around. So, okay, let's do a couple examples. Example 8. Um, Oops, sorry folks, where am I? A patient gave a urine sample which was found to have a pH of 5.7. What was the hydrogen ion concentration? So use my formula. pH equals negative log of the hydrogen ion concentration. Okay, that is 5.7 equals negative log of the hydrogen ion concentration. That's negative 5.7, so I'm going to divide both sides by negative 1. Okay. Convert to exponential form, 10 to the negative 5.7 equals my hydrogen ion concentration. This, folks, 10 to the negative 5.7, let me bring it over here. That's 1 over 10 to the 5.7. So it's a very, very small concentration of hydrogen ions, right? And then this is measured in units of moles per liter. Okay. And this is my hydrogen ion concentration. Okay. Next example. Comparing the pH of solutions. Well, just like we compared earthquake intensities and loudness of sounds, we can compare pH values. Okay, and you can see how all these comparison formulas look so similar. Number 9, pure water has a pH of 7, while seawater has a pH of 8.4. How many times more acidic is pure water than seawater? pH 1 minus pH 2 equals negative log of H1 over H2. Okay, pH 1, 7 minus pH 2, 8.4 equals negative the log of H1 over H2. That's negative 1.4 equals negative the log of H1 over H2. That's 1.4 equals log of H1 over H2. That's 10 to the 1.4 equals H1 over H2. Let's bring it over here. That's 10 to the 1.4. That's approximately 25.1 equals H1 over H2. When we're comparing it, another way to look at it is H1 equals 25.1 H2. So water is 25.1 times more acidic than sea water. Okay, example 10. A river downstream from a chemical factory has a pH level of 6.4 and is 6 times more acidic than a river upstream from the same factory. What is the pH level of the river upstream to the nearest tenth? Comparison, right? pH 1 minus pH 2 equals negative the log of the ratio of hydrogen concentration from 1 and 2. Okay, so 6.4 minus pH 2. Now we're solving for the other pH value, that's negative the log. Well, the ratio, the comparison, it says it's 6 times more acidic. Okay, let's isolate pH 2. So I have 6.4 plus the log of 6 equals pH 2. And then I get, use your calculator, we can estimate this pH of the river upstream. Yeah, so the water, the upstream water, so river upstream from the same factory. So the river upstream, the pH level of the river upstream, the water is 7.2 in pH, right? So interestingly, upstream it's less acidic, and then when you go downstream it's more acidic, so something's being dumped into the river, right? Yikes. Not gonna live near that river. All right, example 11. An apple is 5 times as acidic as a pear. If a pear has a pH of 3.8, then what is the pH of an apple? pH 1 minus pH 2 equals negative the log of H1 over H2. So another comparison. pH 1 minus the pear pH is 3.8, negative the log of 5. So this would be the apple. This would be the pear. So we're solving for pH 1. pH 1 equals 3.8 minus log of 5. So pH 1 equals 3.1. So the apple pH of the apple is 3.1. And folks, that is the end of our unit.